is going to be provided by our CSDA subject matter experts in the area of GNSS radio occultation data, specifically from Spire. I think we have three speakers, and if we can keep it maybe just a little bit under 15 minutes apiece, and we'll have a little bit of time for questions. We're already 5 minutes into things. So I'd like to go ahead and start with Dong Wu, our first presenter. And his presentation is titled A Fresh View of Global Atmosphere and Ionosphere from Combined GNSS-RO Radio Occultation Constellations. Okay, take it away, Dong.
All right, I muted myself. So yeah, you can hear me, right? Good. I'd like to thank this contribution come from a number of authors in Goddard and also Air Force colleague, and funding from various sources make this available. I just want to give a quick overview on what we have so far for the two constellations, Cosmic 2 and Spire. Before I started, so this is a sort of basic geometry of the GNSS-RO. This bending, which is only occur in the very strongly in the lower atmosphere. When you can do the setting or a rising motion. This case is a setting down. I'd like to point out this straight line. Let me using my pointer trick that Jens mentioned. Yeah. So this is a straight line height we can get from the level 1 data, and this is useful quantity. You don't have to do level 2 retrieval. You can plot the data just directly using this quantity. That give you a rough feeling what is the data look like. So in my presentation, I heavily emphasize on the level 1 data. I will give you a couple examples of science later on. For those who haven't seen this data, this is a straight line high. You do radio occultation going down, and you plot the amplitude. So you have two information. One is the amplitude come from radio occultation signal. Another one is a phase, axis phase. That's a actual length due to either bending or due to ionosphere delay. So you can see it's a pretty constant when you don't have lost signal, but when you get to neutral atmosphere, it start to defocus effect. So the signal noise ratio get lower. If you look at the phase, this is where you get this pressure and reflectivity out of that. This is an exponential growth when you go to the bending effect. But above that is ionosphere axis phase. So this is a profile using the two frequency. You can correct the ionosphere and leave the neutral atmosphere, and to get this temperature and the water vapor and lower down. I just roughly point out this is a very mature product, and the rest of them still doing research. People are kind of figured out what is a residual R and how good the quality are. So that's a level 1 data. Hardware-wise, I using a Cosmic 2 give you the ballpark. This is like a cube, meter cube size, and you have two major antenna to receive the signal from GNSS transmitter. One is a pod antenna to give you the position and looking very broad field of view up and down and looking for signal. And another one is a radio occultation antenna with a high gain beam, so you can get tracking very low signal, very directionally coming from the GNSS. And this of course, this technique has been improved recently and especially commercialized by the Spire. Using 3U, they can do that. Of course, when you have a 3U, your real estate is not large enough, but they try to make all the dimension available, like this 3U length to give you the occultation, the high beam for GPS occultation, and with still using pod data to get a high altitude. So this is a rough idea how the two satellites get radio occultation. And this is a Spire advantage. They can send the CubeSat up very frequently, and with right now it's probably dozens of the constellation up there. And as I mentioned, this upper part is ionosphere sampling, and this is a radio occultation sampling, and they can do both ionosphere and a neutral ionosphere. We took a look at the data that delivered from Spire to NASA under CSDA program. This is a level 1B data, just give you a feeling what is this a little bit over 2 years data. They have hardware, they call the flight model number. Roughly, you can see this is a different model they fly so far. And this is for probably the early version. And this is their second version. And they recently launched the third generation, as opposed to a lot of, the reflectivity, reflectometry as well. Just for radio occultation part, if you sum up all the data, this color, by the way, is daily occultation number, occultation. But if you sum them up, you get a steady increasing from the total number available from Spire Constellation. So we are reaching to about, at least in our data archive, is about 18,000 per day. Here is an overview. Go back to 2001. That's probably the beginning of the radio occultation with the CHAM, this NASA German collaboration with this running about over 10 years. This later on come with a Cosmic 1 constellation, so it's a red curve. But that one is start to fade away after 10 years operation. In between, there's a number of small constellation like MAT-OP A and Fengyun and other things, but nothing can make up a significant number like this 6 satellite constellation until the Cosmic 2 and the Spire coming up in 2019 and 2020. And this will give us a total currently, we're talking about maybe over 20 or even 30,000 per day. So this is the current we have. Just give you this is a local time coverage, because not every satellite has a fully local time coverage. And this is equatorial crossing time. You can see CHAMP is processing orbit, so you can get a local time coverage, but gradually proceeding it with the time. And what about this is the other satellite, it's a SunSync satellite. You can see this is a MAT-OP A and B, C, and Fengyun is a SC is kind of drifting away, and other satellites are SunSync. But the Cosmic 1, Cosmic 2, and Spire give you the full-time coverage. And this is very valuable and very important for study the fast process, both in the atmosphere and the ionosphere. This is spatial distribution of the current GPS radio occultation. For Cosmic 1, just a single day coverage, you can see this is back in roughly 2009 for January 1st. And you combine with the other satellite, this is the best you can get for global coverage. And nowadays, with the Cosmic 2, which is equatorial, low latitude, up to plus minus 44 latitude degree, this Spire give you the polar region, but a little bit sparse at the equator. So combines two is very nice coverage globally. So this is about, I must say, you add this together, 17,000 per day plus 6,000. So that's a 22,000 per day. This is a current 2 constellation. And you can see the hardware progression from a meter size, meter cube size, and to 3U. So this is a centimeter, 10 by 10 by 30 centimeter. And also the capability, what you can track the signal. The early time is a GPS signal only, and Cosmic 2 right now is producing the GLONASS and GPS. When Spire is at least really reported the 3 tracking capability. Slightly different frequency, different constellation from those GNSS network. So how much in terms of number, you can see for RO antenna, their Spire give you about 15,000. This is January 1st. 2022. And the pod antenna give you a lot of region in ionosphere, but if you want the whole profile for ionosphere, there's about 6,000 profile per day. And you can use this data to study the lower ionosphere as well. This is useful to give you the sampling. So quickly, I will show you the one example that ionosphere data, where we can use that. So for Spire and the Cosmic 2, we compare the three data, different receiver, different sensitivity. So we see how much, what percentage number can go to the lower atmosphere, lowermost atmosphere, which is we typically very interested in the boundary there, depend on how strong the signal or how good the receiver are. So look at that, the Spire data here, the blue, and the Cosmic 2 are roughly comparable in terms of how many, but the percentage penetrate down to a 1 kilometer level, 85 versus 75-ish. So this is a pretty good that, 3U versus 1 cube, right, in terms of spacecraft. And that's certainly very valuable for studying the lower atmosphere when you have a large variability in there. We also using this data, the lower part of the ionosphere, this is a profile I showed you earlier, the amplitude of GNSS as function of a straight line height. The information from this amplitude here, very low, way below the surface, which is a code behind the Earth. That signal is apparently correlated very strongly with water vapor in the boundary layer. So we wrote a paper about that, and we find we're working on more paper on another paper with this technique to get a water vapor from like roughly a 400 meter above surface. So this is an impressive technique. We think we'll be hopefully to get a marine boundary layer water vapor right in the future. In our ionosphere, the data we took a look at the delivery from Spire, and we applied the technique to do the ionosphere profile, which is the F region, the whole peak here. As you can see, we improved the electron density retrieval, try to improve the lower part of the ionosphere and get rid of this oscillation that they normally using on and peeling, you will suffer from this oscillation. We're using sequential estimation on that. And we apply this for Spire, and you can see this altitude, the Spire satellite, this is a Cosmic 1 satellite. So we think Spire data is very useful for this ionosphere study. And if you integrate the whole profile, you get total electron density. And we did this quick comparison, and roughly they work pretty well. Like I mentioned
Just a few
about
more minutes, please.
Yeah.
Dong.
I'm getting there. This is probably the last
Thank
one.
you.
Yeah, this is a radio occultation. They can be used for ionosphere study. I'm gonna skip on that one. This is sampling is great for this radio occultation. If you map this all the data, you can get a 2-hourly, a monthly map like this for every 2 by 2 degree latitude. So that's all I have. And this is a reference you can read at your leisure.
Thank you very much, Dong.
Yeah.
I suggest that we do questions in the chat and move straight to Jan if that's okay. And then hopefully we'll have some time at the end.
Okay, just want to verify you can see my slide.
Yes.
Okay, yeah, good afternoon, everybody. I'm Jan Weiss with the UCAR Cosmic Program. This is work I'm summarizing that's mostly done by my co-authors who are listed here. We have Rick Anthes, Yuri Cherniak, Shulai Feng, Teresa Van Hove, Irina Zaharenkova, and Janet Zheng. And we've been looking at the Spire radio occultation data for both the neutral atmosphere and the ionosphere products. Okay, I'll have a little bit of introduction and background and then jump into some comparisons of the Spire products to Cosmic 2, as well as a three-cornered hat analysis, and then we'll move on to ionosphere results for total electron content. So Dong already gave a nice overview of RO, so I don't need to spend any time on this other than to say that we'll first be looking at the neutral atmosphere retrievals and then total electron content above the neutral atmosphere. All right, so we've been quite interested in the CSDA purchased Spire data. One thing that's very nice about it is that it's, I believe, the whole data set, everything that they are collecting from the Spire constellation. So it should really give you a representative view of the performance of the constellation. And I'll just point out, this is in contrast to the NOAA purchased Spire data, which we also process in near real time for operational and science users, but that is a subset. It's currently about 6,000 profiles a day out of, it looks like they're around 15,000, collecting around 15,000 currently. So so this is very nice to have access to these data because we don't have to wonder about whether we're only seeing the very best profiles as is possible with the NOAA data. So for these analyses, we focused on January 2021, and we're looking at both the Spire products, that is the products that we can download from the CSDA site generated by Spire, and then we also downloaded the lower level observation data and generated our own level 2 products in the CDAC framework, the Cosmic Data Analysis and Archive Center. And just point out that we're only able to retrieve about 76% of the profiles that they provided. That's mainly due to we don't have all the precise orbit that so that's sort of the main reason for that. Okay, so this is starting to compare some of the data sets for the neutral atmosphere. So we're going to use the Spire S for the Spire processed product, and then Spire C for the CDAC processed product. And then this is a look over the whole month of January at the penetration. Dong just showed something like this as well. And you can see that Cosmic 2, about 87.5% of the profiles reach 1 kilometer. The CDAC processing about 83.5, and a little bit lower, 78.5 or so for Spire processed by Spire. So the first two are handled consistently because they're both run through our system, and Spire is doing some things differently. We don't know the details, and so they get a little bit lower penetration, or out of the total number of profiles. So this is the looking at the whole data set for the month of January, and then we're going to look at some comparisons where we're pairing the data. So here, this is a particular day. This is representative, and here the Spire produced and the CDAC produced data are matched in terms of time, as well as the reference satellite used and the RO satellite that the data are coming from. So in terms of some interesting features here, so the top is, or the top left is the bending angle bias versus ECMWF, where the CDAC produced version is the black line and red is the Spire produced version. The standard deviation is up here on the right, so you can see some differences. In particular, up high, there's a higher standard deviation for the Spire product than what we're getting. That's up high, so above 35 or so kilometers, that starts to become more and more apparent. Then the bottom panel is again bias on the left and standard deviation on the right, and this is just for 20 kilometers and below. And we can see that you were getting maybe a little bit lower bias here between 3 and 6 kilometers or so, but a little bit higher standard deviation, sort of in a similar range. And then the counts are over here. This is 1 day, so it's not the full month. We looked at some QC parameters, so this is something we'll incorporate, but we did notice that we can tune a QC parameter that we flag, which is measuring the relative deviation of the bending angle versus a climatology background in the 20 to 40 kilometer range. If that fractionally exceeds 25%, we flag it as bad. In our system, that's sort of a default, and we decided that one thing we can tune is to loosen that up a little bit, and then we'll get a bit more Spire data through with our processing, and we'll have to evaluate that, but we think it's going to look reasonable after that change. Okay, now switching gears to looking at the data in a little bit different way. So this is the three-cornered hat analysis. Some of this group will probably be familiar with the work that Rick Anthes and Jeremiah Schilberg and Shulei Feng have been working on over the past years, comparing 3 or more data sets using this technique. And it's a very nice approach. So we have basically a truth. We'd like to know, this is just a simple data model, the truth. Then there's a bias error, and then there are sort of random errors. And hold on, I'm trying to somehow get my WebEx window out of the way here. Okay. And if I'm only going to go through this quickly, but basically if you have 3 or more data sets, you can compute the random error variances from an equation like this. And this is for one of the, you need data sets X, Y, and Z. The equations are similar for each of them. If the correlation between the data sets is 0 or nearly 0, then this should be a very good measure of what is the real random error for each of the data sets that you're combining. So that is assumed here in this analysis. There's papers out there that talk about this in more detail. We believe that that's basically true in these cases, and it's a nice way to also estimate errors. So what we're going to show here on the next couple of slides is the Spire processed Spire data compared to our processed Cosmic 2 data, and we will be adding the CDAC processed Spire data to these results, but it wasn't ready for today. Okay. So this is a plot. I'm just going to focus on the refractivity here since it's sort of nicely marked up. The dashed lines are the estimated random errors, standard deviations for Cosmic 2. The solid lines are for Spire as produced by Spire. The colors are red is for the GLONASS profiles. Black is GPS and GLONASS combined, and then green is the GPS result, and that's the same for both data sets. And so you can see again that somewhere around 30 kilometers, these start to diverge, and the Spire errors are estimated to be greater by up to a few percent, especially up high here. And that below, they're really quite consistent. So that's sort of consistent with the prior results that we showed. The differences between GPS and GLONASS are mainly due to the transmitter clocks. So the GPS clocks are more stable at short time scales. So we see that effect here. And that's been something we've seen in Cosmic 2 all along. A little bit different view. This is now the Spire uncertainty minus the Cosmic 2 uncertainty estimates, again for black being GPS and GLONASS, red being GLONASS, and green GPS only. So, this up high, the Spire uncertainties were clearly bigger, so there's the positive curve, and then they start to become fairly close to 0 at 30 kilometers or below. We do find an interesting feature here that the bending angle estimate for Spire is actually smaller than Cosmic 2, between roughly 3 and 8 kilometers, while the refractivity estimate is bigger for Spire. So that's something we're trying to understand. We think this is related to how the vertical smoothing and the retrievals is done by the 2 different processing centers, but we're still working on evaluating this feature. Okay, so then moving on to the ionosphere. So we looked at slant total electron content, or TEC, produced by Spire, and then also by the CDAC system, again for January 2021. And we assessed the stability and temporal variation of the differential code biases, which we have to estimate in the processing, and Spire does that as well in their processing for the receiver code biases, and then the TEC statistical distributions. And we found that in order to judge a TEC product from a satellite to be good and reasonable for use in science applications, that we would like at least 1 million points over the month per satellite from the Spire data, about half that from our produced TEC, and that we have reasonably low ages for the DCB estimate. So generally, these are estimated in our system every day. Spire is doing them in a different way. Sometimes they're much older, so we're not sure of the details there, but it does make an impact on the results. So some examples here from the Spire products. So I'll start on the right. Actually, these are the DCB estimates for a particular satellite by day. And you can see those are fairly consistent throughout this month. Down on the bottom, we have some estimates for only a few days, and they're quite old in this case. So they were not very fresh estimates. So that's one of the parameters in the product file that you can read. And then correspondingly, the distribution of the TEC points, I'll start on the bottom here, is fairly ratty in this case. So you can see this is not a very nice sort of Gaussian looking distribution, and it has a lot of negative points here. The fraction of negative is quite high, so that's a flag that these are not very good TEC estimates in this case. Whereas the top you can see is a much nicer looking distribution with a smaller tail on the negative side. These are then some two examples from our processing for 2 satellites over the month. These are good examples with nicely distributed, nice looking distributions, I should say, with small negative tails. And the DCB stability is a bit different between these satellites. So there's from top, the envelope is about 5 tech units here across the month for this satellite, and roughly double that for this satellite here. And it seems like there's sort of a gradual change. And this can be related to, probably various factors. And they definitely change over time. So that's why we estimate them every day. Okay, and then this is just an example table in the backups. I've got all the satellites of basically our assessment of the TEC data by satellite. And you can see they mostly match up, and then some of them are a little bit different. And it turns out overall that we found that 25 of the FMs produced useful and usable TEC products from the Spire data set, and we ended up getting 2 more. But generally, these are quite consistent, these results. All right. So then to conclude, so we've taken a look at the nice complete Spire data set for a month in this case. We definitely find that the data processing and the quality control procedures that are used will impact the product counts, the penetration of the RO profiles, and the estimated uncertainties. We'll be adding to these results here in the next month and have a little bit more detail. So probably not a surprising result there. In terms of our in-house processing, we are able to get most of the Spire data to be generated into useful products. We find that our penetration is a bit higher or lower in altitude, I should say. And our uncertainties are a bit lower, in particular at the higher altitudes than the Spire product. We have identified a couple of things that we can tune in our processing. From the 3-corner hat analysis, we also find that the Cosmic 2 has deeper penetration than the Spire data. That was shown. We find smaller uncertainties above 30 kilometers than the Spire product. Down lower in the troposphere, a couple of mixed results, but generally quite consistent, I would say, between the 2 processings. And on the ionosphere side, we generally get reasonable TEC results from both data sets. We do find some differences in the computation of the DCBs and how often that's done. And that impacts our judgment of the sort of goodness for each FM. And we get a little bit different results. And then just finally, a couple of lessons learned. This is something I've mentioned previously. We'd like to hopefully have a little bit easier way to download the data in the future. This website is very nice, but when we have thousands of files per day, it's a little bit cumbersome to fetch data. So perhaps a daily tar file or something could be arranged in the future. That would be great. And then for the processing, so I mentioned the 76% number, that's the fraction of RO profiles that we were able to generate from the data provided. The main reason for that is that the precise orbit determination data do not always cover at least a couple of hours around each occultation. And that in our system, at least, it gives us processing and QC issues with our POD. So that's the main reason for that difference. So maybe that's something that can be looked at with Spire to perhaps provide a little bit more POD data. And then on the QC, we've identified in particular one parameter that can be tuned, and I think we'll get a few more good quality profiles on the neutral atmosphere side out as a result. So hopefully I didn't run over too much, and I guess I'll turn it back over to the moderator.
Okay, thank you very much, Jan. Again, let's go ahead and put the questions and comments, if you have any, in the chat. And let's move on to Nikki, if we could.
Sure. Let me... All right, is the PowerPoint coming up?
It sure is.
Excellent. All right, so this is some work that actually took several years to do and involved a group of people. The biggest helper here was Ron Errico, who is now retired in doing this work. All right, so we've already had some overviews in the previous talk about how the GPS, the GNSS-RO observations work. So we're getting here these radio occultations that give you soundings of temperature and humidity. So what we're going to be looking at here in this talk is using these soundings of temperature and humidity in numerical weather prediction. So there's been some interest, in the past couple of years, increasing interest from the community in launching large numbers of GNSS satellites. So the question that we're going to look at here today is there a saturation of information that can occur? Is there some point where you have so many of these satellites that you're not getting that much use out of the data anymore? So we're going to be doing that using an Aussie, and I'll get to Aussies in a second. So I'm going to go briefly on about how numerical weather prediction uses these observations. So normally how numerical weather prediction works is you have a set of observations and you have a guess from usually a model about the current state of the atmosphere. And that guess is generally a forecast that was made from a previous time. And then we use data assimilation, which takes the observations and the forecast and basically squishes them together with statistics and produces an analysis. And this analysis is statistically the best guess as to the current state of the atmosphere. And that analysis uses the initial condition to make a new forecast. So then 6 or 12 hours later, you have your new forecast, you have some new observations, and you repeat this whole process over again. So the data assimilation uses a weighting to weight the observations and the guess, the forecast. And depending on how much error the data assimilation thinks the observations have and how much error it thinks the forecast has, it'll do kind of a glorified weighting average of the observations and the forecast to combine them together statistically. So what we're going to do here today is an OSSI, an observing system simulation experiment. And this is an experiment that you use when you don't have real data. So you want to do this when you want to look at how a future system would impact numerical weather prediction. And to do this, we replace the entire real world with simulation. So first we replace the real atmosphere with what we call a nature run. This is a long free model run, and it's used as the truth. It's considered the real world for the purposes of the OSSI. And then we simulate observations. we don't just simulate the new observations that we're interested in, we also have to simulate all of the other observations that are used by the numerical weather prediction on a daily basis. Okay, so we have to simulate the aircraft, the ray wind sondes, the satellites, everything. So we make these simulated or synthetic observations, which are usually done by interpolating the nature run fields or using operation operators. And then we use, in our OSSI, we add some errors. We simulate errors and add them to our simulated observations because these errors are important in how the data assimilation system weights the observations. And then we take these observations and we treat them just like real data. And we assimilate them into a different operational model than the one that was used to make the nature run. And we can do experiments with them because everything is simulated. We can use this as a very sophisticated kind of toy to look at all kinds of different combinations of potential future observing systems. Okay, so we have in-house at GMAO a global OSSI setup for numerical weather prediction. We have simulated observations for microwave sounders, for hyperspectral infrared sounders, for microwave humidity sounders. We do all the conventional types, ray wind sondes, aircraft, AMVs, surface data. We add errors that are both totally random, uncorrelated, and random correlated errors in order to try to match the error statistics that we see with the real data. For the GNSS-RO, we simulate the RO data from the nature run using the raw 2D operator, which has ray tracing below 10 kilometers. But we assimilate with the data assimilation system in our experiments using the one-dimensional grid point statistical interpolation, or GSI operator. So we're using a different method to simulate the RO data than we're using to assimilate it. And this will introduce a portion of additional error into our observations. And we do add some both uncorrelated and a little bit of vertically correlated error to the RO data. The data assimilation system we're using is the hybrid 40 on VAR GSI, and we're doing these 2-month experiments with a model running, the GS model running at 25 kilometers. So this is what system I'm going to use for all the results I'm going to show you here. So the experiments that we're doing here, we're looking at these saturation experiments to see if we add a very large number of RO observations per day, do we see this drop off in usefulness of the data? So the top left panel here is showing you for a 6-hour cycle how many RO data observations we have in our control. And you can see that we don't have very many. Our control was based on 2015, the year 2015, and it was kind of a low point when there wasn't actually that many RO data. And then we have 4 experiments where we add up to 100,000 additional RO soundings, profiles per day. Okay, and this is just showing the locations for a 6-hour window. For our 4 experiments is of 25, 50, 75, and 100,000 additional RO data profiles. Okay, so for the results here, the first thing I'm going to show you is the impact of adding these new RO data on the analysis, which was that combination of the first guess with the observations. So this is basically the initial condition for your forecast. And in these plots here are showing you the zonal mean, root mean squared, error of the temperature analysis compared to the control. So what this means is if the error is reduced compared to the control when you add more RO data, it's going to be negative and it's going to be blue. So blue is good, meaning that you've added the RO and it's gotten improvement, and red is bad, meaning that when you add the data, you actually worsen your your analysis state. Okay. And you can see here that as we increase the number of RO data, that we see a stronger response. The blue parts get bluer, and unfortunately there's some red parts, the red parts get redder. So we're definitely having an improvement in the temperature in the upper troposphere, in the lower stratosphere, and in much of the southern hemisphere, but we're actually seeing a degradation in the temperature in part of the northern hemisphere. And there's 2 things happening in the northern hemisphere. There's one of the things, the big dark red blobs that you see down in the lower troposphere. This is something that occurs only over marine Arctic surfaces over the Arctic Ocean, and we suspect this is due to a boundary layer, very strong boundary layer inversion. It's the summer in the Arctic. It's July. It's August. The data assimilation is having trouble using the data correctly in the vicinity of this strong inversion. So that's our suspicion for the very dark red blobs. But this lighter pink area that is occurring more in the northern hemisphere and a little tiny bit in the southern hemisphere, from 40 north up to the pole and a little bit near 40 south, is, we suspect, due to a possible misweighting of the observational error characteristics of the RO data by the data assimilation system. So I'm also going to show the forecast impact. These plots are showing up to a 7-day forecast. So the x-axis is the forecast day. This is the normalized for the global, the entire globe, the normalized reading square temperature forecast error versus control. The stippling indicates 90 percentile significance, and this is normalized, so it's a fraction. So negative 0.1 is a 10% fractional improvement in the temperature forecast error. So we can see here that the largest impact is occurring at the initial time, in the first 1 or 2 days. But we do see a retention of this improvement all the way out to day 7, especially for the larger numbers of RO data. Okay, but it's kind of a little spotty and a little weird looking. So I'm going to break this down for you regionally to look more closely at what's happening. So here I've broken down that same plot, which is now in the upper left, into 3 other regions. So we've, instead of using the entire global region, we're looking at the northern hemisphere extratropics in the top right, the southern hemisphere extratropics in the lower left, and the tropics in the lower right. And this is all for the 100,000 additional RO case, okay, just so that you can see it more clearly. For the southern hemisphere extratropics, the one that's all blue, this is the kind of behavior you'd probably expect to see. You add a lot of nice new data, it has a strong improvement, and it manages to retain an improvement all the way out to day 7, throughout the depth of the troposphere. In the northern hemisphere extratropics and the tropics, though, we see something different happening, especially in the tropics. Initially, in the first day or 2 days, we see a strong improvement, but then suddenly it switches over and you see a degradation. That red is showing the degradation of the temperatures. What we think is happening here is there's a difference in the convective scheme between the nature run and the forecast model. And after the first day, there's a response where the model starts to convect a lot and starts precipitating. And when it does this, the temperatures, the temperatures change in response to this strong precipitation and convection. And then that actually is the cause of this degradation in the temperature field in the forecast at these 2 layers, at the upper troposphere and the lower troposphere. In the last metric I'm going to show you here, we have a tool with our system called Forecast Sensitivity Observation Impact. And this tool is a kind of a quick way to put all of your observations in perspective with one another without having to run a whole lot of data denial cases. So this is kind of a proxy estimate for data denial. And what we're looking at here is an estimate of how much influence the observations have on the 24-hour forecast of global total wet energy. Okay, so it's one specific metric, but all of the observations, how all the observations affect that. And you can see here, the yellow is for the 100K, the darkest blue is for the control. The RO data is on the topmost in the plot here. And you can see that as you increase the number of RO data, that you have an increase in this total observation impact, okay? And once you get up above, actually, once you put in 25,000 RO soundings, you're already matching the same as AMSU-A, which is like 5 or 6 satellites, and all of the AMV observations, and more than the ray obs. And as you keep increasing the count of the RO, you do get more impact, but you can see there's kind of a reduction. You get a really big jump in the impact going to 25K, and then a smaller jump going to 50K, and then a smaller and a smaller. So there's definitely seems to be a diminishing return once you get especially above 50,000 additional RO per day. All right, so our quick takeaway here is that we do seem to see a little bit of a tendency to level off in the impacts once you especially get past 50,000 RO data. And we do see some issues using these data. We've seen some issues with the analysis where we saw there was areas of red degradation that seemed to be coming from how the data assimilation system is handling these observations. And our recommendation would be to go back and think about, should we change how the weighting, the error weighting used by the data assimilation to try to improve how these observations are used. And we've seen that there's also these possible feedbacks coming from the model, especially in the tropics in the summer, in the southern hemisphere, which is the northern hemisphere, and in the tropics related to this precipitation feedback, where you can get these unfortunate impacts. And we have a recent paper that just came out, if you want to see this and many more plots and all the gory details. This just came out in Monthly Weather Review a couple months ago. So if you're interested, you can go ahead and check that out. That is the end of my talk.
Okay, thank you very much, Nikki. Let's see, I don't see any questions right now in the chat. If you have a question, go ahead and raise your hand, and hopefully I can figure out how to see hand raised and hands raised. Here we go. Jan, I think you have a question.
Yeah, for Nikki, I was curious, did you compute FSOI per observation? And if you did, what did that look like?
We do have it, and I have to tell you that I don't remember offhand. But we do have those plots available, and if you're interested, I could send them to you.
Yeah, thanks.
Let's see, I have a question. So I guess we're seeing diminishing returns at the 50 to 100,000 observations. And I've forgotten, I think either Jan or possibly it was Dong that showed how many observations we have at this point. Could somebody remind us of that number?
About 22,000 per day.
Okay, great. So there's still room to grow there. Okay, maybe just give a couple more minutes here in case there's any other questions. I certainly want to thank the presenters and also those who attended. So not seeing, oh, wait a minute. Okay, we got some applause. That's what we have here. Okay. Yeah. I think not seeing any more questions. I guess we can go ahead and finish up. Thank you again for the presentations and for attending.
Thanks, everyone.
Thank you, Fritz.
And
Thanks.
thank you.
Thank you all.